Okay, today we're going to do section 1.6 in the IM2 book and talk about exponential functions. These functions are very useful in real-world situations. They're used to model populations, karma date artifacts, help coroners determine time of death, compute investments, depreciation, and on and on. So you'll see just some examples of different kinds of exponential functions here. So they're kind of cool. Okay, in this slide it tells you that how to notice that an exponential graph is increasing. So notice over here that we have a straight line graph, a linear graph. That represents steady increases. It's going up at the same rate all along the line. Okay? But an exponential has a curved graph because it's showing that it's happening at a faster and faster rate. Okay, it's like when you put when you start a car and you start going down the road, the speed is going to increase. That's what the rocket's doing. Okay, in an exponential function, the independent variable is the exponent. Here's a graph of the basic exponential function, the f of x equals 2 to the x. The way they write it algebraically is to write it like this. We don't use a 1 here because 1 to any power is 1, so they can't use it that way. Okay, so this is the basic parent function you'll almost always see for exponential graphs. What is the domain and range? The domain, we know that the lines go on forever unless it's a word problem, so the domain would be all real numbers. The range is y is greater than or equal to 0. You have to be very careful with exponential functions because they get closer and closer but never cross the x-axis unless they've been translated up or down. The basic parent function, like I said, is this one, where b is the base. Using x and y values from a table, you simply plot the coordinates to get the graphs. The parent function of any exponential function that has not been translated crosses the y-axis at 0, 1. Why do you think that is? Think about the basic graph. When x equals 0, what is this going to equal? Anything raised to the 0 power equals 1. The characteristics of a graph of an exponential function, which is f of x equals bx, they all contain the point 0, 1, again, unless they've been translated. The x-axis is always an asymptote, again, if it hasn't been translated. The asymptote is the line to which the graph gets closer and closer to, but never crosses. A graph is decreasing if b is greater than 0 but less than 1. The graph is increasing if b is greater than 1. The rate of change increases or decreases across the graph. This is an increasing rate of change. This is a decreasing rate of change, meaning the rate of change is getting smaller, as we go down. Now, here's a picture of some graphs that have been translated. They start with the parent function here, and then they graph it this way. Okay, this just defines an asymptote a little bit better. It is the line that a graph gets closer to, an exponential graph gets closer to, as the absolute value of a variable increases. In IM2, we will only look at asymptotes on the x-axis. So, for example, and a graph will get closer and closer but never touch its asymptote. So here's the parent function, which we've already shown, and our asymptote is y equals 0 because our line is going to get closer and closer but never cross the x-axis. This graph was translated up 3. So our new asymptote is y equals 3 because our graph is going to get closer and closer to the line y equals 3 but never cross it. This graph, the third graph, was translated down 3. So my asymptote is now y equals negative 3. Our exponential graph will get closer and closer to y equals negative 3, but it will never cross that line. Okay, an exponential function has a form a b to the x, when a does not equal 0 and the base is a positive real number other than 1. If a is greater than 0 and b is greater than 0, then it's a growth function, and b is called the growth factor. The simplest type of exponential growth function is the one we've been looking at, y equals b to the x power. Okay, you can look at this, all of this in your textbook or in your journal. Okay, so this is showing you the explanation for a decay. If b, so if y equals abx, if b is in between 0 and 1, in other words, it's a proper fraction, then it is an exponential decay function, and it will look like this. Okay, so this is just an example of what you can expect. So when you're given an equation like this, then you're going to solve it by going 2 to the negative 2, which means you have to flip it, so it's 1 over 2 squared, so the answer is 1/4. 2 to the negative 1 is 1 over 2, so it's 1/2. 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 4, and 2 cubed is 8. So I'm going to graph that. Negative 2 to the 1/4 would be right about there. Negative 1 to the 1/2 is there. 0 to the 1, 1 to the 2, 2 to the 4, and 3 to the 8. So I'm going to graph this like this. Remember, you don't want it to get close. Okay, so now I'm going to do this one. I have 1/2 to the negative 3 means I have to flip it, so I get 2 to the 3rd, which is 8. 1/2 to the negative 2 is 2 squared, because I flipped it, which is 4. 1/2 to the negative 1 is 2 to the 1, which is 2. 1/2 to the 0 is 1. 1/2 to the 1 is just 1/2. And 1/2 squared is 1/4. So now I'm going to graph this one. Negative 3 is 8. That's up here. Okay. Negative 2 is 4. And when I put solid circles, it always messes the instructions up to the board. And this is 2. And this is 0. Whoops, 0 is 1. So this is 2, sorry. And 1 is 1/2. And this is 1/4. And so this one looks like this. So I just want, but getting closer and closer. Okay? So I just wanted to show you the two differences between those. So they should cross at 0, 1. And that's how you would draw them. And that's how you figure them out. Okay, so now we're going to talk about exponential models and recursive rules. That's recurring rules. So some real-life quantities increase or decrease by a fixed percent each year, or each month, or each week. The amount of y of such a quantity after t years can be modeled by one of these equations. So if you look at this, the A here represents the initial amount. That might be dollars, it might be temperature, might be something else. R is the percent increase or decrease. If it's R plus 1 plus R, it's a growth factor, or 1 minus R, it's a decay factor. So the purpose of the 1 is to include the initial amount. For example, if I was doing interest on money in the bank and I had the 1 plus the R and I calculated out, I'm going to know how much total money I have in the bank. But if I only have the R and not the 1, it's only going to tell me the interest. So that's why we want the 1, because we want the new amount, not just the change. Okay, so writing an exponential model. So the population of a country was about 6.09 million on this date. The population at the beginning of each subsequent year increased by about that much. So write the exponential model. So here's the growth model that we're going to be using because they're saying it increased. That's your clue. The y is the population in millions, which we don't know what it is, but the a was the initial population. And the r, our rate of increase, is this. Remember how to change percent to the decimal. And now we calculate our new recursive model. Okay, so now what we're going to do, we've got all that information. A is find and interpret the y value when t equals 7.5. That's a mid-year population. So what you're going to do first is you're going to add these. You get 6.09 times 1.0118 to the 7.5. So now you're going to put that in your calculator and you have to calculate this first. We did parentheses, now we're doing exponent, and then we go back and we multiply 6.09 times whatever that calculated out to be, and we get approximately 6.65 million after 7.5 years. Okay, so that's a big jump. That's an increase of about 0.54 million people. Okay, now the second one was estimate the population, estimate when the population becomes 7. In other words, you're finding t. Now, if you go to the example in the book, you will see that they show you how to use the table feature on a graphing calculator. So you can go back to page, this example in the book, and it will show you how to do that. Okay? But otherwise, we would just have to estimate, and we can't really solve that. Later on, you'll learn how to do logarithms. I think that's how you spell it. Maybe it's a Y. Anyway, you'll learn how to do that, and you'll be able to solve this kind of problem. But the answer that you'll get is about 11.9 years, which is near, so you'd have to add that to 2011, the year 2000, and you'll get 2011. And so it'll be 0.9 of the year, so it's near the end of 2011. Okay, so now you're going to do some problems on your own. Remember, this one you don't need to do unless you have the graphing calculator and you know how to use it. So this one is optional. So I will work these out at the end. So go ahead and start working on these. Hit the pause button, and the answers will come up in a minute, and we'll go over them at the end. Okay, so we're going to go over these at the end, but here are the answers. So circle them if you got one wrong so you can see what you did wrong. Okay, when you're writing a recursive rule for an exponential model, it's important that you know what is expected, and you have to do all of this. If you don't show this part, you're not giving the recursive rule. So the first thing you have to do is find out what is the function when x equals 0. So looking at our example that we just did, we would put a 0 in for t, and we can see that if t was 0, then our function, this would equal 1, right? If this is 0, this becomes 1, and this is f equals 0. So there is the initial value, f is 0. Now, the second part, you need to understand that this is not the rate of change, it is the common ratio. Okay, and the common ratio is everything that's inside here. So it would be that whole thing. And then this part never changes, it's always times f to the n minus 1. So this is what you have to do to get the recursive rule for any problem. Okay, so now they want you to do number 6. I'm not going to push the pause button. I'm going to go through these with you. So the first thing I see is to find the f of 0. I put a 0 here, okay, and 6 to the 0 is 1, so that equals 2. And then the rest of my equation is the f of n, and it's going to come up, so I'm just going to show you that in a minute. So this is my ratio, so I would go the f of n equals 6 times the f of n minus 1. Okay? Over here, I have the f of t, so I have to find what is the f of 0. If I make this equal 0, then it's 11. This whole thing is my common ratio, so I would go the f of n, the f of n equals 0.3 times the f of n minus 1. And here they are written for you nice and neat, but that's how I got them. Okay, now we're going to learn how to rewrite an exponential function to determine if it's growth or decay. So we're going to start with this. The first thing you need to know is before you can decide if it's growth or decay, this exponent can only be a t. It can't have anything else attached. So what we do is remember the rule of a to the x times a to the x equals a to the x plus x. So now we're going to do, and I just showed you that here, t to the fourth equals 1/4 times t, so we're going to separate it. And we're going to put the 1/4 inside the parentheses and the t on the outside. Then you're going to calculate the fourth root of 0.96, and that is 0.99. And I can see that this is less than 1. This would be 1 minus 0.01, so this is decay. Okay? All right, let's try a different one. Okay, now for this one, we're going to remember the rule of the same one we used before, so we're going to separate them. We're going to put 1.1 to the t times 1.1 to the negative 3. And you could put this one in front, commutative property, it's okay. Then you're going to calculate this. Be careful when you calculate it. This is what it looks like. So if I calculate this, I am going to get 1.331. Do not think you are done, because this is actually 1 over 1.331 times 1.1 to the t. Okay, so now what I have to do is I have to, in order to finish my equation, I can see that it's going to be growth, okay, because it's 1 plus 0.1, but I have to figure out what my equation is. So in order to get this number that's outside of this part, I have to do 1 divided by that number, and that equals 0.75. So that is your final thing, and that's the step I wanted you to make sure you didn't miss. So it's growth. Okay? Alright, so you guys are going to complete these problems. You're going to figure out if they're growth or decay by simplifying the statements, and you push pause, and then we'll go over these at the end. Okay, so here's your answers. If you didn't get them right, circle them, and we'll come back to them at the end. Last thing I wanted to include in this video was a real-life problem that is in your book, and it's all about depreciation. The value of a car is $21,000 when you buy it, this car. Okay, it loses 12% of its value every year. So what? Okay, the reason why that's important is, one, if you want to resell the car, you know that you can't sell it for this amount. But another thing is, if you were a business and you had a whole fleet of cars, you are going to depreciate the value of those cars because those are your assets, and that depreciation is tax deductible. Okay, so that's why depreciation is so important. So here is the problem as it's worked out in the book. So the rate of decay is 12%, so you go 1 minus 0.12, and that gives you your equation. And then they went on to find a couple of other examples to find solve problems. And that's how the value of the car goes down. Okay, so the value of each car is going to be going down, is maybe going to have a different decay factor, because a more expensive car might go down in value less. If you buy a classic car that's all fixed up, it might not decay, it might go up in value. So you've got to know all the information about your car. Okay, so go through this problem in your book to learn more about depreciation. So that's the end of the video, and now I'm just going to go over those few problems that were done in the middle. Okay, so I went ahead and worked these out because I didn't want to torture myself, but just so you can see, what I did was I said 3 over 2 to the negative 2 would equal 2 over 3 squared, and that's how I got the 4 to the 9th. So you can go ahead and figure those out, and then you would graph them, and the graph would be negative 2 is 4/9, and negative 1 is 2/3, 0 is 1, 1 is 1 1/2, so this isn't going up very fast. 2 is 9/4, so that is 2 1/4, and 3 is 3 3/8, so this is going to look, I'm not hitting my dots at all, so there you go, something like that. Okay, so number 4, this is 1 minus 0.2, so this is decay. Oh, and this was growth, obviously. Okay, and then for this one, this again is optional because you'd either use the table function or you'd have to estimate over and over again. It's kind of a pain. So this is growth because it's 1 plus 0.99. And is it an hourly increase? What is the hourly increase or decrease? That's the rate of increase. So it's 99% increase per hour. All right, okay. For these two, number 8, you're going to go 3 times 1.25 to the 4 times 1.25 to the 4th. And the reason you're going to do that is because it's t plus 4, so we know that we're multiplying the bases by each other, and that one should be a t. Okay, so now I'm going to calculate this one, and I get 3 times 2.4414 times 1.25 to the t, and then I'm going to multiply this, and I get 7.3242 whatever times 1.25 t, and I can see that it's growth. But you need to get the whole equation simplified because it's saying rewrite the function. So when they tell you to rewrite it, you have to finish, not just get to the point where you can see the t by itself. Okay? Number 9, you would do 0.44 to the 7th times, no, to the t, like that. So that would give you, because these are multiplied, okay? So since this is plus, you do it this way. If they're multiplied, you do it this way. So it's going to be 0.44 would be 0.00319 to the t, which is decay. And we are, do we have one more? Nope, we're done for today. Thanks.